Welcome to lecture 15 of our system protection course. In the last lecture, in lecture 14, we talked about the reactance relay, which is also another type of distance protection, which also used for another type of distance protection. So in reactance relay, already we have seen that the current in fact provides the operating torque and the directional element provides the restraining torque, and already we have seen how we can implement this kind of relay using an induction curve structure, induction curve electromagnetic relay. And also we have seen the performance analysis of reactance relay during the normal load condition, during the power swing, and also we have discussed about the directional property of the reactance relay, and already we saw that it has no directional property, and also during power swing it trips. Even with a little power swing the relay trips. And the only advantage we have observed in the reactance relay is that it provides the better performance under arc fault condition, because most of the faults in practice are arc faults. So under arc fault condition its performance is very good because the underreach is 0%. So therefore it is most of the time when we use the reactance relay along with the impedance relay or Moore relay, it is preferred. So let us see the next type of relay, that is Moore relay. So already we covered impedance relay, and also we covered the reactance relay, which are part of the distance protection. In this lecture we will cover the Moore relay. So let us see what is Moore relay, and in fact how we can implement this, and how the performance of Moore relay is, whether it is better than impedance relay, reactance relay, or it is less. It is the performance is not good as compared to impedance relay and reactance relay. So let us first consider the universal torque equation. Already, as the flow is, first we consider the universal torque equation, and from the universal torque equation we derive the trip law for different relays, right? So again we'll do it for Moore relay. So this is your universal torque equation, right? Already we can see here, that is k1 ir square plus k2 vr square plus k3 vr ir cos theta minus tau plus k4. So this is the torque due to current, this is due to voltage, this is due to the directional element, and this k4 is due to spring. Already we have discussed this in the beginning, and in this case let us consider k1 as 0. Okay, so put k1 0 and k2 as negative and k3 as positive. Okay, so that if we'll set k1 equal to 0 and k2 negative. K2 negative, what it means? K2 negative means, in fact, it provides the restraining torque, right? Okay, and if we'll put K3 as positive, let us make K3 as positive. So K3 positive means your directional element will provide a positive torque. Okay, that means operating torque. So here in this case your directional element is providing the operating torque, and your voltage element, that is providing the restraining torque. Okay, so now as we will go ahead with this, as K3 is positive, so as I told, this directional element will provide the operating torque. So K3 VR IR cos theta minus tau should be greater than K2 VR square in order to operate the relay. So when the relay need to be operated, this should be the condition. and the relay can thus be described as directional relay with voltage restraint, because directional relay with voltage restraint, right? So directional relay, why it is directional relay? Because the directional element, in fact we'll see in the next slides how it is a directional relay, but from this equation itself we can say that because the directional element is the operating, it provides the operating torque, therefore we can call it directional relay, and the voltage element is providing the restraining torque, therefore we'll call it with voltage restraint, it is a directional relay, right? Okay, so therefore I can write this equation as k2 Vr squared less than k3 Vr Ir cos theta minus tau. Just from this equation I can get this equation, and again from this equation after rearrangement I can find Vr square by Vr Ir less than k3 by k2 cos theta minus tau. So after again rearranging this, I will find Vr by Ir less than k3 by k2 cos theta minus tau. So Vr by Ir is nothing but it is the Zr, which we call it the impedance seen by the relay, right? Impedance seen by the relay. Okay, so this is Z sin or Zr, that is less than k3 by k2. k3 and k2 they are constants, it will depend upon the constructional feature of the relay. And cos theta minus tau, theta is the angle between the voltage seen by the relay and the current seen by the relay, and tau is your uh, torque, maximum torque angle, right? So maximum torque angle is the angle between the maximum torque line and the voltage seen by the relay VR, right? So that means your, if Z sin is less than Zn, so I can write this K3 by K2 as Zn, which is the setting of the relay. So Zn cos theta minus tau, then it will trip, else it will restrain. Okay, so this is the trip law for Moore relay, that is Z sin less than Zn cos theta minus tau, then it will trip, else it will restrain. Now we can see in this figure that very nicely, actually Zn is making an angle of tau, right? Okay, so and your Zr is making an angle of theta, because theta is the angle between Vr and Ir, right? So theta is the angle between Vr and Ir, right? So therefore Zr will make an angle of theta with respect to R, that is R axis, right? That is reference axis. Or you can say the resistance axis. Okay, and similarly your Zn is considered, it is laying along with the maximum torque maximum torque line, and which is making an angle of tau, and your Vr is in fact lying in reference with the R axis. So we are considering Vr as the reference signal, okay, here. So therefore now the angle between this Zn and Zr will be theta minus tau, right? So now if we'll see Zn, if I'll plot Zn uh, Zn cos of theta minus tau, then obviously OB will be your Zn cos of theta minus tau, right? So this OB will be Zn cos theta minus tau, and if your Zr is lying, or Zr is less than this, that is Zn cos theta minus tau, then it will trip. That means wherever the Zr will lie, it doesn't matter, right? If your angle remaining fixed and your voltage and current magnitude is changing, maybe your point will lie here somewhere, or maybe it will lie outside this, right? So therefore when this will become greater than this Zn cos theta minus tau, right? So then it will be trip, and it will restrain, right? it will restrain, and when it will lie within this, that means ZR is less than Zn cos theta minus tau, then it will trip. It is a trip region, right? How the circle is made, we can see this, how the circle is made. So this theta will change as we change the theta. Okay, as you will suppose remaining keeping the tau constant and change the theta. Now if we'll plot this Zn cos theta minus tau by changing theta and keeping tau constant. Okay, tau constant. If we'll plot Zn cos of theta minus tau, right? So these points will gradually will get this like these points, right? Which will make 90° to OA. Okay. So if your theta will change, it will obviously like this. It will make these points, right? So if we'll plot for all theta, then it will make a circle. If we'll connect all these dots, it will make a circle like this, right? So that gives the operating characteristic of the Moore relay. So this is your, in fact, operating characteristic of the Moore relay, right? So this will be the operating characteristic of the Moore relay, which is nothing but a circle. Okay, operating characteristics of Moore relay. Okay, now we have seen. We can also check the directional property here, right? So this is your VPC. This is nothing but your equal to VR, right? Which is the voltage seen by the relay, and this is the angle. This is ICC, which is nothing. Sorry, this I can write here VR. So this is ICC, which is making an angle of theta. We are considering here the directional relay, right? ICC is equal to nothing but IR, that is the current seen by the relay, which is making an angle of theta. And similarly, if I'll plot IPC, that is current flowing in the pressure coil, and that is making an angle of theta PC, right? And I can plot the MTA line, that is maximum torque line, and I can plot the trip and restraining zone. Okay, so that means your trip zone is here and restraining zone is there, right? So this is your MTA line, this is your MT line, right? Maximum torque line. So now perpendicular to that, if I'll plot a, just let me erase it so that it will be clearly visible. Okay, so now if I'll plot this perpendicular line with respect to the empty line, it will be like this. It will be like this. Sorry. Okay, and this is your, in fact, trip and restraining region. So you can see here, considering the directional property, your whole operating characteristic, in fact, lying in the trip region of the directional element, right? So therefore, the whole region of the whole circle is lying in the trip region of the directional element. And in addition to that, the circle itself, it covers a very less area, and which in fact shows the trip region, right? Okay, so therefore more relay is, the advantage is here, it has a directional property and it covers very less area, okay, as compared to the reactance relay and the impedance relay. Okay, so this is the added advantage of the Moore relay. And let us see the implementation of the Moore relay using the induction curve structure. As we have seen the implementation of reactance relay using the induction curve structure. Here the only the connection will be little different. We can see here this is your restraining voltage coil, right? And we have polarizing voltage coil which will in fact support in developing the restraining and the operating torque, right? So the you can see here, because the voltage coil is in fact it will act as the uh, restraining part. It will develop the restraining torque. Therefore the interaction of the flux produced by this polarizing voltage coil and the restraining voltage coil will in fact produce the uh, restraining torque, like here and here, both the polarizing voltage coil and the restraining voltage coil. And similarly the operating current coil and the polarizing voltage coil, in fact this will be your directional element, a combination of these two, operating current coil and the polarizing voltage coil. So these two will combine give us the operating torque. So now I can see this is your operating torque, right? Okay. So operating torque will be developed by the interaction of the flux produced by the operating current coil and the polarizing voltage coil, which in fact combinedly known as the directional element. And the restraining torque will be developed by the restraining voltage coil and the polarizing voltage coil, both, right? So therefore uh, it will produce the restraining torque, right? So this is the simple operation of uh, Moore relay when we implement using the induction curve structure, right? So let us see the performance of Moore relay during the normal load condition. As I have already shown that, already I talked about this, that under normal load condition, I already I told that operating point will lie somewhere here, right, near to the r-axis. Okay. Now, uh, if we'll plot the operating characteristic, it will look like a circle, right? And if we'll see, it will cover very less area in the first quadrant and very fraction of areas in the second and the fourth quadrant, right? And therefore you're always under normal operating condition, the operating point will lie outside the trip region in the restraining region. Therefore there is no chance of relay operation, mal operation of the relay during normal load condition, like in case of reactance relay, there is always chance of mal operation during normal load condition, but here it is, the case is different, right? Okay, now we'll see the effect of arc resistance and Moore relay, how it will in fact impact. Already we have seen the effect of arc resistance on impedance relay and reactance relay, and we have seen that there is some underreach problem in impedance relay, and in case of reactance relay there is no underreach problem. Similarly, here also we have underreach problem. In fact, we can see the underreach, if we'll calculate the percentage underreach, obviously it will be AB by uh, AO into 100, right? In fact, the setting is here, OA, right? OA is nothing but, OA is not Zn, it is in fact Zn cos of theta minus tau, right? So Zn is this, sorry, this is not Zn, this is your Zn. OC is your Zn. Okay. So then obviously your uh, your percentage, this will be your tau, this is theta. Okay. So theta minus tau, cos of theta minus tau. So therefore your percentage under reach will be AB by AO into 100%. So in fact here, as compared to the impedance relay, the Moore relay has little more underreach as compared to the impedance relay. So therefore, sometime in the combination of Moore relay and reactance relay as provides the good performance under this condition. Okay. So directional property exhibited by Moore relay. Let us see the directional property. Already we discussed this directional property. Already I told that this part is the trip region for the directional element. This part is your restraining zone for the directional element, and your circle will lie in the that operating characteristic of the Moore relay always lies in the trip region of the directional element, right? Like you can see here, right? This is your operating characteristic of the Moore relay, right? Operating characteristic of the Moore relay. Sticks of the Moore relay. And which is lying, we can see very clearly that it is lying exactly within the trip region of the directional element. So this is your this is the operating characteristic of the directional element, right? This is your operating characteristic of your directional element of directional element, right? So, and your Moore relay characteristic is lying in the trip region of the and in fact this, if we'll say this is your superset, right? Superset, this is your subset, right? That means Moore relay trip characteristic is subset of the uh, directional trip characteristic. Okay. So now let us see the performance of Moore relay during power swing. Already we have seen the power swing performance in case of impedance relay and the reactance relay. In case of impedance relay, if your power swing is very high, then it comes inside the characteristic, and if it is in fact low, it remains outside the trip region, uh, that is in the restraining region. But in case of reactance relay, whatever may be the power swing, little power swing, it will maloperate the relay, right? The reactance relay. But in this case, as we can see, considering a transmission line which is double fed, right, with source EA and EB, EA and EB, and the source impedances are ZSA, ZSB, and transmission line impedance is ZL. If we'll plot the swing locus, that power swing locus on RX plane, already we have already discussed this, how to plot this locus, right, by deriving the equations. So no need to derive here again, but this is the locus. As your delta will increase, it will go towards this, right, and also from this side, and as your delta will decrease, it will go towards this, away from the operating characteristic of the relay. So this is your trip characteristic, right, and this is your restraining. This is in fact inside, it is trip, right? And we can see, as compared to the impedance relay and the reactance relay, the operating or the trip characteristic of the Moore relay is very small, and it covers very small area, and therefore the power swing will be detected when it is very severe. When the power swing is very severe and it becomes critical, in fact, it goes inside the trip characteristic of the Moore relay. If it is not, then it remains outside, therefore there is no chance of maloperation in case of Moore relay. So no maloperation during power swing. Okay, as in case of as it happens in case of reactance relay and your impedance relay, there is a chance of maloperation, right? Okay, so this is how your Moore relays plays important role as compared to impedance relay and the reactance relay. So let us see a comparison between distance relays. So already we talked about impedance relay, reactance relay, and Moore relay. So we talked about the uh, characteristic equation, then we plotted the characteristic in Rx plane, then we saw the performance of the different relays under different conditions, under normal load condition, arcing fault condition, under power swing, and also during the normal load condition, already I told. So let us see the comparison, right? So we have seen three relays. One is your simple impedance relay, reactance relay, and more relay. Right. Now let us see compare these quantities. The quantities are here mentioned here, right? So first quantity we'll compare is your operating quantity. So what are the operating quantity in case of simple impedance relay? The current is your operating quantity. Similarly, in reactance relay, already we have seen the current is your operating quantity, and in case of more relay, the directional element is your, uh, in fact, your operating quantity, right? Similarly, if we'll consider the restraining quantity, in case of restraining quantity, for simple impedance relay, your voltage is your restraining quantity, and for reactance relay, your directional element with MTA equal to 90° is your restraining quantity, and in case of more relay, your voltage is your restraining quantity. And if we consider directional property, then simple impedance relay doesn't exhibit a directional property, no. And similarly, your reactance relay also doesn't provide any directional property, therefore no. And your more relay provides the directional property S, right? We will consider the performance of these three relays under normal load condition. Then your simple impedance relay restrains and your reactance relay trips. Already we have seen this under normal load condition, and your more relay also restrains. And in fact, your more relay performs better than the impedance relay under normal load condition. Then we'll see the effect of fault resistance in case of simple impedance relay. Obviously it underreaches, already we have discussed this, and in case of reactance relay the reach is unaffected, and in case of more relay in fact it is there, the underreach is there, and in fact it is more than the simple impedance relay. And the last but one, sorry, it is the area occupied on the Rx plane, how much area it occupies. The simple impedance relay operating characteristic, it occupies moderate area, but your reactance relay occupies very large area. Therefore, there is a problem of this operation under a normal load condition and power swing condition. And the smallest area is occupied by the more relay, right? Already we have seen this. And if we'll see the last one, that is effect, it is the most important effect of power swing on different relays, the most important, last but one but very important. So the simple impedance relay maloperates sometime, but your reactance relay it always maloperates, and your more relay maloperates sometime, and the effect is very less as compared to the simple impedance relay. Okay, so it maloperates sometime, it is not always, right? Okay, so this is the great comparison. Therefore, more relay is most of the time preferred relay in the distance protection. Okay, so we'll stop here. Thank you very much. In the next class, we'll also continue the distance protection. We'll see in the next class how we can implement in a three-phase system, how we can implement this distance protection or distance protection schemes. I will talk about more. So thank you. Thanks a lot. Thanks for your kind attention.